Well, I'll say good morning to everyone. So we've been talking about aberrations. And the last class we were talking in particular, we were talking about Seidel aberrations. And we talked about spherical, which I told you was my favorite. But it wasn't your favorite. Your favorite was down here when we get to coma. Has anyone changed, have you changed your mind over the weekend? Long weekend, you had a chance to? No? Okay, well, still coma. And then we had poor astigmatism here, which no one seemed to like. Anyone have astigmatism as your favorite? No? Oh, that's too bad, sorry. And I'm worried about the next two. Field curvature. I don't know if I can, I doubt if I can talk you into field curvature being your favorite. But anyway, maybe I can make that a little bit larger though, so I can see it a little better. So field curvature, W220. So it's, well, rotationally symmetric. We have the zero at the end here. Goes as a field to the second power, x naught to the second power, and it goes as rho squared. So it's like curvature, like focus. But the problem with it is that it's a focus shift, but the focus shift depends upon the field, and it varies as a square of the field. And so it's really saying we're going to get if we have no other aberrations, we'll get a very good focus, but the focus will be on a curved surface that we often call the Petzval surface. So, well, I mean, that's a problem we have. It's not something in testing that we measure too often, but sometimes you do. And you might think here for a second, you know, astigmatism also went as a square of the field height, so sometimes people will group these two together. So that's about all I was going to say about field curvature, so I'm sure I haven't convinced you that that's your favorite aberration. But I'll come down to distortion. Maybe I can convince you that's your favorite. So distortion goes as W311. So it goes as a field to the third power, and rho to the first power, cosine theta to the first power. Or we often just write it as W311 x naught cubed times x. So it's just a tilt. And we can calculate what the shift in the image is by finding epsilon sub x, as we were doing in the last class, minus r over h partial of delta w with respect to x. And we get a term here, then it's just minus r over h, W311 x naught cubed. So it's not really just a change in magnification, it's a shift that is proportional to the field position, proportional to the image height, and it goes as a cube of the image height. And well, I have a couple of pictures down below I'll look at here. So let's say we have an object that looks like the little squares on the left there. And when we image that, if we have distortion, well, lines going through the center here will still remain straight, although their length will be either shorter or longer, depending upon whether the coefficient W311 is greater than 0 or less than 0. And if you have a line in the object that doesn't go through the axis here, then that's going to be curved, because again, it's field dependence goes as a field position cubed. And so if W311 is greater than 0, then the image is going to come in like this, and we often call that barrel distortion. And if W311 is less than 0, then things are stretched out here, and we call that pincushion distortion. Okay. Now you probably have all seen this in images. Just about a week ago, I bought a a webcam from Amazon, which I really liked the webcam because it was working with, works with Wi-Fi. So I could put it around my house any place I wanted, and then I could check up on things from my computer. But the problem with the thing, it's a very nice webcam, except the barrel distortion is just unbelievable. I've never seen so much in my life. And I was so upset with it, I thought I'd send it back. But then I got thinking, you know, where else could I find such a great demonstration of barrel distortion? So I'm going to keep the camera. And but every time I look at it, oh, I get sick. Okay. So let's vote again. How many say of the 5 of the Seidels here, how many are going to say spherical is your favorite? Raise your hand. Oh, this is bad. Whew, one. Only one A in the course, I think. How many say coma? Yeah, a few. Oh, maybe there's hope here. Stigmatism. Oh, one person. Wonderful, wonderful. Field curvature? Oh, couple. Fantastic. And then distortion. Oh, distortion really came back strong today. That's great. Okay. Spherical hasn't done so well, though. But remember, I'm the one who makes up the test, so maybe you'll change your mind on what your favorite is. Or maybe it will become your least favorite. I don't know. Okay, so those were the Seidel aberrations, which I'm sure you've seen a few times before, and we'll see a few more times. Next, we'll talk about Zernike's. How many of you have studied Zernike polynomials in other courses? Good. Okay, so do you like Zernike's? A lot of people like Zernike's. In fact, I used to say, you know, there was time in my life when if you could just spell the word Zernike, you could get money from the Air Force, because the Air Force loved Zernike polynomials. And you could write a little proposal to use them for anything, and oh, they gave you money. But I'm afraid those days have gone away. But it was that way for a while. So anyway, we often like to express the wavefront data in some polynomial. And the polynomial that is probably most used is Zernike polynomials. And the reason is you see that the form is the same as the types of aberrations that you often see in optical tests. And so Zernike's can be pretty useful. I think in the early days of doing computer analysis of optical testing results, Zernike's became very popular because you typically would only measure a wavefront at a few points. You know, maybe 100 points would be a lot of points for measuring over the pupil. And in doing the analysis, you really wanted to have more points than 100. And so that's where people really got used to using Zernike's to fit to your data, and then you be easier to work with. But now, in many tests, I mean, you do the measurements at 1 million data points or 4 million data points or more. And so fitting of polynomials and doing interpolation is less important, although you generally fit some polynomials to find how much tilt you have or how much focus or spherical or coma and so on. The thing is that Zernike's, they really are pretty good for fitting a lot of data that you get in optical tests. But if you're doing something here, like I mentioned, a single point diamond turning, where you have may have some grooves in the surface, then the polynomials will not fit that. Or if you're testing or measuring something in the presence of atmospheric turbulence, the Zernike's, although Zernike's have been used for that, they don't work very well. And so you really, as I put here in blue, I guess, that just the blind use of Zernike polynomials may get you into deep trouble. But I want to spend a little bit of time talking about the Zernike's. And we're not going to go through the math so much as to look at some results. And One feature that we're going to find that's going to be very interesting, or very useful maybe I should say, is that the Zernikeys are orthogonal, in a continuous fashion anyway, over the interior of a unit circle. By orthogonal, what we're saying here is that if I have I fit a few Zernike terms, and then I get the coefficients for these terms, and then I decide, well, let's fit a few more terms. As I fit the additional terms, that since these are orthogonal, the fitting of the additional terms will not change the fitting to the first terms that I fit to. We'll talk a little bit more about that in a minute. The point here that I'll stress a couple of 3 times is that these Zernikeys are orthogonal only in continuous fashion and only over a unit circle. And so if I have a discrete set of data points within a unit circle, the Zernikeys are not orthogonal over this discrete set of data points. Or if I have an optical system with a central obscuration, which is pretty common, the Zernikeys are not orthogonal over that. It's orthogonal over the unit circle, but if you have a central obscuration, they're no longer orthogonal. Now you can go through and find another set of Zernikeys that will be orthogonal over the particular aperture you have, and sometimes people do that. Well, I guess that's just, again, saying they're orthogonal down here. There's I'm going to give you some of the terms for the Zernikeys in just a minute. The terms are fairly easy to calculate, and there's a generating function here where you plug in your n and m's and s's, and you can calculate the different terms. And then you can write the wavefront as typically some average value, and then you have terms that depends upon rho, and you have terms that are going to rho to some power, and you're going to have terms that depend upon rho to a power and then a cosine and sine. And these a's, b's, and c's are the coefficients for the polynomials. So anyway, you could go through here and you could calculate the polynomials. I'm going to give you a list here, and I'll have to say the ordering of these polynomials, it's not the same for everyone. And the mathematicians have their ordering, and people like myself who work in interferometry generally use this particular ordering of them, but you want to, wherever you work, you may have a different ordering of the polynomials. I like this particular ordering here, where we start off with what I call number 0 for some reason, but that's just a constant polynomial that we'll write as 1 here, and then there'll be some coefficient times that. And then the next two, which according to my numbering is 1 and 2 here, will be a rho cosine and a rho sine. And so these are what? Tilt terms. So this would be like an x and a y. And as I say here, that's then a tilt. The next one down here, which turns out to be 2 rho squared minus 1. So the rho squared is a focus or defocus term. Then, there's a minus 1 here, so it's a piston term we're dropping. And that's there for a few reasons, but one is that makes this term orthogonal with respect to the first term here. It's orthogonal with respect to all the terms, but had to add in a minus 1 to make it orthogonal with respect to this one. But that just comes out in your generating factor. So this would be a focus term. The next one, a rho squared cosine 2 theta and a rho squared sine squared 2 theta would be it's a stigmatism term with some defocus added into it. And we'll see some contour maps in just a second on that. And so it's just the right amount of defocus, it turns out, to be orthogonal with the lower terms, and in particular the focus term here. Then the next two, 6 and 7 here, 3 rho squared minus 2 rho cosine theta, and then same thing but sine theta. That's a coma and a tilt. Okay? And so again, the tilt's added to make it orthogonal. So these two are coma and tilt. And then we come to, of course, my favorite one here, the 6 rho to the 4th minus 6 rho squared plus 1. And so that's what, spherical aberration. And then we're subtracting from that some focus. And then we're adding a constant term to it. So those are the first 8 plus the piston term. And then, so these would be like our third order aberrations. And then the next group here would be the fifth order aberrations and the seventh and so on. And however many you want to keep out here. Well, for my table anyway, I go out to 36 plus the constant term. And the 36th one, we actually skipped quite a few in here. To get just to the rotationally symmetric one. So we have some pictures here of what the different terms look like here. And so, the tilt terms, and then a curvature term, stigmatism and a defocus, coma and tilt, and third order spherical and defocus. And we could keep going down here if we wanted to look at all the higher order terms if you want. And again, want to, you could go up to the website here and you could find, I put 35 Zernike here, and it's a little slow at calculating. Let's see if it's going to calculate it. Finally did. What I like about these pictures, you can rotate them. But if I press the letter S, which stands for stereo, then you have stereo pairs, and you won't be able to see it from your seat. But I can see it very nicely on my computer here, and I can fuse the two together and see 3D quite nicely there. Or if you want to get the density plot, get that. And you might note that the default here came up to be spherical too. But anyway. Okay. So if you go through and look at these in detail, as I said before, each term contains the appropriate amount of each lower order term to make it orthogonal to each lower order term. So as you fit higher and higher terms, it's not going to change the coefficients for the lower order terms. Now that's true, again, I'll say it one more time, continuously over the unit circle. And if you just have discrete data points, which you normally have, then they're not really orthogonal over these discrete data points. And so some of the coefficients for lower order terms will change as you fit higher order terms. The other thing is, this is actually very useful here. I said each term of the Zernicke's minimizes the RMS wavefront error to the order of that term. And adding other aberrations of lower order can only increase the RMS error. Also, the average value of each term over the unit circle is 0. But as far as the RMS goes, if we come back here, and this says, if I look at spherical, it goes 6 rho to the 4th minus 6 rho squared plus 1. So that says that if I have spherical aberration, so I have a rho to the 4th term, if I want to minimize the RMS, the root mean square of the wavefront, then I want to introduce an amount of defocus that is equal in magnitude and opposite in sign to how much spherical I have. So every wave of spherical, I want to have minus wave of defocus to minimize the RMS. While if I have coma here, that says that for every 3 waves of coma, I want to subtract 2 waves of tilt. And you could go through each one of these with that type of analysis. So that turns out to be a very useful property of the Zernike's. Okay. So you're beginning to love Zernike's? If people gave you money just for, if you were able to spell the word Zernike, would you like them better? No? Sorry, those days are gone. Well, the Zernike's look a lot like the third order aberrations. So sometimes it's convenient just to find a relationship between the two, and you simply write down the Zernike's, and you can pick out the pairs that correspond to the third order aberrations. And I go through a little algebra here, which I know that all of you will go through it in your room, in your office later today, but I'll just give the results down here, if I can find them. And so the Z1 through Z6 are the coefficients of the Zernike's. And so if I want to go from how much tilt I have from, calculate that from the Zernike's. I mean, this shows that the magnitude, it shows the results anyway. You can go through the derivation if you want to. That it just goes as square root of Z1 minus 2Z6 squared plus Z2 minus 2Z7 squared. So that gives you the magnitude of the tilt. And then the angle of the tilt is the arctangent here of what, Z2 minus 2Z7 over Z1 minus 2Z6. So I'll let you go through and derive that. It's not too hard to do. Focus turns out to be this. I mean, you had focus terms in Z3, Z8, Z4, and Z5. And this is the way of putting in the calculating the magnitude of or the amount of focus you have. Now, there's a plus and minus sign here. This kind of groups here with the astigmatism, because some of these terms come from the terms where you had astigmatism. And I put here that the sign is generally chosen to minimize the absolute value of the magnitude. And so it could be a plus or minus. And then depending what you put here, you'll change something down here in the astigmatism. Because astigmatism is just curvature in one direction, and you could, I mean, you could write that as a curvature in this direction, and then minus an astigmatism in the orthogonal direction. And I say the sign is chosen to minimize the absolute value of the magnitude. Actually, that's not often used anymore. Generally, just the minus sign is normally used here. Now, depending on what sign we pick here, then we have a little bit of difference down here in the astigmatism. And if we pick a plus sign there, then we have to have a minus sign down here. And then I hate to say it, but I have an error in this book chapter, that if we pick the minus sign down here, then the angle is actually 1/2 arctangent of Z5 over Z4 plus pi over 2. I forgot the pi over 2 down here. And let's see. So I just put in a note there that if we use a minus sign for astigmatism, we add the pi over 2 to the phase. And so not only are we changing the sign of the astigmatism term, but we're rotating it by 90 degrees. So anyway. And coma you get from the Z6s and Z7s. And this gives you the angle of the coma. And spherical, you just have one spherical term. That's one's easy then, just 6 times the coefficient C8. So any question here? So almost any commercial interferogram analysis program you use to analyze your interferograms, they often will fit to Zernike's, at least for the first 8 terms here. And then from the Zernike's, they'll calculate the Seidels. Okay. Peak to valley and RMS. Well, people often like to have one number that tells you how good this optical system is. And sometimes that number they use is a peak to valley. So they'll measure the wavefront aberration produced by the optical component of the optical system. And they'll find the maximum departure of the wavefront in, say, the positive direction, and the maximum departure in the negative direction, and then just take these two and find the peak to the valley. Like I guess for the example I give here, I say, let's say the maximum departure in the positive direction is 0.2 waves, and the maximum departure in the negative direction is minus 0.1 waves. Then the peak to valley would be 0.2 plus 0.1 or 0.3 waves. And that's easy to do, and it's often used. But of course, the problem with that is that we're really looking at just 2 data points and determining whether the system is good enough by just looking at 2 data points. And so you can generally get into, or you can get into some trouble doing that. Still used, though, quite often. A somewhat better way is to go over and calculate the root mean square error of the wavefront. And so we would just take the wavefront here. I'll subtract from that the average value of the wavefront. We'll square that and integrate that over the pupil. And so if we kind of look at this, what does this calculate here? It's just going to be the delta W squared average value over the pupil minus delta W average squared over the pupil. When you do the multiplication here, the cross terms are going to cancel out because we're subtracting out the average value. And so this would be our sigma squared, the variance here. And so often you'll just go through and do this integral. And it's certainly very simple to do on we have the data, very simple to do that on the computer. If you're expressing this wavefront aberration in Zernike polynomials, it turns out, and I'm not going to attempt to prove this today, but if we go back to the A's and B's and the N's and M's in the used in calculating the different terms of the Zernikes, it turns out that sigma squared is given by this quantity right here. And so if you have the Zernikes, it's very fast and easy to calculate sigma squared from that. So the A's and B's and N's and M's, let's go back here and look just what they are. Can I find them here? So the A's and B's are the coefficients here for the rotationally symmetric and the non-rotationally symmetric terms. And the n's and m's are the what was used in a generating function, and so they're just the n's and m's in this table here. So from the coefficients and n and m's, you can very easily calculate sigma squared if you want to from the Zernike's. If I can find it there. But I almost always anymore, the calculation's so easy just doing this calculation up here that I would probably just do this. But back in the days when computers were slow and stuff, we would often calculate it this way. Okay, so RMS is probably a better way of describing how good an optical system is. So that takes us to Strehl ratio here, and we're going to see a very nice relationship between RMS and Strehl ratio. Yeah. Mm-hmm.
So when you give the Zernike's in that table where you have, the piston tilt defocus terms all the way at the top, are those peak to valley Zernike's? Yeah, these ones?
No, that's just a coefficient, just a term, and then there'll be a coefficient times that. Now,
so if you're given this term, would that be in terms of, would that just be peak to valley coefficient?
the coefficient here could be whatever you want. Normally maybe waves, or it could be nanometers. It could be, so there's a term. I mean, the coefficient is multiplied times this term right here. And so you would go through here and calculate these coefficients, and then you might say, well, the coefficient for Z8 here is 3 or something, 3 waves.
Okay, so then when you went back to go calculate for instance, to get the spherical out of that, and you calculated spherical using the table below this,
Yeah. Mm-hmm.
would that would then be a peak to valley?
That would be how much spherical you have. It would be, I can come down here to find the right place. That would be that you have a tilt of some amount, whatever, if you used waves here, and if this came out to be 5.2, then you have 5.2 waves of tilt. So the W11 coefficient would be 5.2. Okay. Yes?
Question. Maybe it's related to his, but I've seen the Zernike terms before with a normalization constant in front of them. I was wondering what's a typical way of normalizing this one?
There are 2 ways of normalizing these. One way is to normalize them so each one has the same RMS number. And so you'll see a term here in front of it. You'd see the terms that I have and then multiplied by something else, like square root of 3 or square root of 5 or something. It'd be different for the different terms. And that's normalizing to the RMS. I did not put that normalizing factor in here. I was going to find but I had another comment here. Maybe I don't have it. No, I did not put that normalizing factor in front of it. So, but some places you'll see that. Well, I guess equal weighting of the coefficients by RMS would be why people do it. I'd have to admit, in the work that I've done, I've never normalized them to RMS, but I think it's just so each term You know, if RMS is a quantity you're interested in, maybe it's convenient to see them expressed in terms where each term has the same RMS value.
Is there any other way people normalize them, or if you see
I think those are just the two ways. It's just what I have here, and then the factor in front that takes care of the RMS, normalizing RMS. The other thing you do see often, though, is that they are in a different order than what I put them here. And I actually had a student who convinced me many years ago, this student by the name of John Loomis, who convinced me that this was the proper way to order them, because we were grouping the, you know, we're looking at the side-L aberrations here, and then the higher order terms, the same thing. But mathematicians sometimes like to group them different ways. So you just have to be careful if you're getting data from someone else on Zernike's. You just want to make sure that you understand how they have ordered them compared to the way you might order them. And different programs will order them different ways, yes.
So if you have the error based on the normalized way where you get the RMS, RMS error from the coefficients, is there any trick to that where you could generate the overall RMS error based on all those without having?
Yeah, that's a good question. I mean, the RMS, I'm sure the answer is yes, but I don't know just exactly how to do it. But if you, I don't know. I'd have to look at it. If you, what did I have the, I mean, it falls right out of, if I can find this equation right here. I have some other notes. I think I put the other notes up on the web where I give what the coefficients are to normalize for the RMS. If you can't find them on the website, let me know, and I have them on my computer for sure. Any other questions before we go on? Okay, stereo ratio is a very interesting quantity. And how many of you have seen stereo ratio before? Quite a few of you. Okay. So, I'll just say, in the absence of aberrations, I use the word intensity. I wish I'd used the word irradiance, but I use the word intensity here. But I'll say irradiance is a maximum at the Gaussian image point. And if aberrations are present, then this is probably not true. Probably the maximum irradiance is at some other point. And the point of maximum irradiance is what we call diffraction focus. And so we probably will have to add in some tilt, which is, so we're moving our point we're looking at transversely, and we're adding in some defocus, so we're moving our observation point longitudinally to get a wavefront variance that's a minimum, and we're going to see that's going to give us where the irradiance is a maximum. Irradiance on the irradiance at that particular location is a maximum, or in the image is a maximum. So we define here the ratio of the irradiance at the image point in the presence of aberration divided by the irradiance that would be obtained if no aberration was present. We call that the stereo ratio or stereo definition. And so to calculate what the irradiance is, you just sum up the e to the I 2 pi times the aberration over the pupil. And we put in a pi squared out in front that's going to normalize this. So if I have no aberration and a uniform circular aperture, then this stereo ratio will turn out to be 1. And if I have some aberration here, then this is going to reduce what the stereo ratio is. It's going to reduce the irradiance of the image point. And I see I forgot to show this table when I was talking about RMS, so let me go back for a second and just look at that. Just made a little table here of for defocus and spherical and defocus and so on, and calculating the RMS wavefront aberration. And so, like for defocus, we write the aberration would go as W20 rho squared. And the RMS then turns out to be 0.289 times whatever this coefficient W20 is. If I have spherical, W40 rho to the fourth, this will turn out to be about the same. It's 0.298 times W40. The interesting thing is that if I now take my spherical and add some defocus to it, and if I add, for every wave of spherical, if I add or subtract one wave of defocus, then my RMS goes from 0.298 W40 down to 0.075 W40. So adding in the defocus greatly reduces the RMS for a spherical aberration. And the amount of defocus we added in, well, I made it equal to the amount of spherical, but minus a sign. And why did I pick that number? Because I noticed that we said that one property of the Zernike's was that it added in the appropriate lower order terms to minimize the RMS. And so here, and we saw that for spherical, it was, we wanted the same amount of defocus as we had spherical, but opposite sign in order to minimize the RMS. And it does greatly reduce it down to 0.075. Astigmatism, 0.25. I put in some defocus here, brings it down to 0.2, 354 times the coefficient here, and coma plus tilt will bring it down to about 0.118. Okay. So, I'm sorry, I had forgotten to mention that when I was talking about RMS up above. Back to Strel ratio here. So we're just integrating over the wavefront over the pupil and finding then what the maximum irradiance is. We're finding out what the irradiance is, and we're normalizing it, so if I have no aberration, this Strel ratio would turn out to be 1. Well, I could take this e to the I, 2 pi delta w, and I could expand that if I wanted to. And so we'll expand that here. So that becomes a 1 plus I, 2 pi delta w, plus so on. Now, the Strel ratio, so that's giving us the peak intensity with the aberration divided by what it would be without aberration. It's really a quantity that's useful only if we have a small amount of aberration. A Strel ratio is somewhat close to 1. And so a small amount of aberration, I can throw away the higher order terms here. And I could just pick this pick it so the third order and higher order terms of 2 pi delta w I can throw away. And if I do this integral here, I think for a second I'm going to get something at, well, 1, it's normalized here. And then there's a term that's going to be I 2 pi times the average value of delta w. And the next term will be, turn out to be a 1/2 and a 2 pi squared, so on. Delta w squared averaged. And then this whole quantity here will be squared. And so what that really is just 2 pi squared times delta w squared average minus delta W average squared. And that, if we go back and look at sigma, that was just the quantity for sigma. And so the Strehl ratio here, I mean, this is an amazing and very interesting result here, is that the Strehl ratio is approximately equal to, for small wavefront aberrations, it's approximately equal to 1 minus 2 pi sigma squared. Sigma being in units of waves here. Independent of what the aberration is. As long as the aberration is small, the Strehl ratio here goes as 1 minus 2 pi sigma squared, independent of what the particular aberration is. So isn't that neat? So this gives you another reason why probably expressing how good an optical system is in terms of the RMS might be pretty meaningful, because it related right directly here to Strehl ratio, which related to the what the peak intensity in the image would be with aberration divided by what it would be without aberration. Okay. Now, this calculation here is valid for Strehl ratios as low as about 0.5. So it's good between 1 and to 0.5. And it turns out, if you go through and don't throw away all these terms, that the Strehl ratio is always just a little bit larger than what's predicted by this equation here. And it turns out that a better approximation, for most types of aberrations anyway, is simply the Strehl ratio goes to e to the minus 2 pi sigma squared, where sigma is units of waves. Okay. So it'll be e to the I 2 pi sigma quantity squared. And if you multiply that out, you get something like what we had up above, and except the higher order terms. And I said this was always a little bit too small, and so this kind of compensates for that. And this works good down to Strehl ratios about as small as 0.1. So there aren't many equations in the world you should memorize. But I would say that this right here on the Strehl ratio, these two right here, 1 minus, well, I think of this as 1 minus RMS squared. And then this one here, e to the minus 2 pi sigma squared, are useful. Okay? Any questions? Well, when is a system good? What Strehl ratios are reasonable? There's an old criterion by Marichal, who was a professor at the Institut d'Optique in France, who says that a system is regarded as well corrected if its normalized intensity at diffraction focus is greater than or equal to 0.8. And that corresponds to an RMS wavefront error of lambda over 14. Now, whether that is still a good number or not, certainly the people in lithography would laugh at you and say they would never put up with a Strehl ratio as low as 0.8. So it depends on your application. So this is maybe not, nowadays, maybe not quite as stringent as what people might want to use. But Anyway, that's still a commonly used criterion. And just going back here, repeating again, I said that each term of the Zernike's minimizes the RMS wavefront error to the order of that term. And so you're adding in the appropriate number of lower order terms to minimize the RMS. And so if you try to add in other aberrations to lower order terms, you're only going to increase the RMS. And just repeating again that for my favorite term, the Zernike, 6 rho to the 4th minus 6 rho squared plus 1, we say that for every wave of third order spherical, you want to subtract 1 wave of defocus to minimize the RMS. And so to find the maximum stereo ratio, to find diffraction focus. Okay. Any questions? Yeah, maybe the Zernike's are worthwhile after all. Chromatic aberrations. I always spend 30 seconds talking about chromatic aberrations. So really, when we talk about chromatic aberrations, there are 2 different types. You have the chromatic variations in the paraxial image forming properties of a system. And then you have the wavelength dependence of the monochromatic aberrations. And that's generally the first type here that we talk about here, the chromatic variations in the paraxial image forming properties. So we have 2 here we'll talk about. We have the longitudinal chromatic aberration. So the focus here will depend upon the wavelength. And typically here the index is higher for shorter wavelengths, and so the blue here would come to focus, and with a singlet like this, the blue would come to focus in front of the red. So it bends the blue light more than it does the red. If I think about diffraction, in diffraction, what angle or what wavelength is diffracted a larger angle? Would it be the red or the blue? D sine theta is m lambda, some equation like that, I remember. So the longer the wavelength, the more the light's diffracted. So just the opposite between diffraction and refraction here. Maybe we can make use of that at some point. So that's the variation of focus with wavelength. We also have a variation of magnification with wavelength. We call that lateral color. And so here with our lens forming an image of something or another here, the size of the image will be different for the different wavelengths. And that's everything I was going to say about chromatic aberration. Okay. Now, why would I talk about aberrations introduced by plane parallel plates? Well, the reason I talk about it is that this has absolutely driven me crazy over the years. Because in a test setup, all the time, you're putting in a window, you're putting in a beam splitter, you're putting in these plates that are either parallel surfaces or close to parallel surfaces, and they always do bad things. And I pulled most of my hair out because of plane parallel plates and problems I've had with plane parallel plates. And I don't want you to have the same problems. So I want to talk about them here. So we'll first talk about a longitudinal displacement. So now I have a window in my test setup, and I'm imaging through that window. And lo and behold, the image is not where I thought it was. it's going to be shifted a little bit here when I put in the window. And the amount of shift in this window, I mean, you can see what's happening when the light strikes a window, higher index than outside. So the rays are going to get closer to the normal. And when they come out here, they'll be parallel to where they were when they went in. But inside the plate, where they were closer to the normal, is going to cause this image to be shifted some distance here. And the amount of shift here, if you go through the calculation, which I think all of you, either you've done this or you will do it today when you go back to your office, that the longitudinal displacement turns out to be refractive index minus 1 over the refractive index times t. And so we could calculate what the shift is. The thing that some people think about this, though, is that this window, I mean, it has some actual thickness, but it has some effective thickness. And so we say, what's the effective thickness of this plate compared to air? Well, it's less than the actual thickness because we get this shift here. And so the actual thickness is T, and the shift is n minus 1 over n times T. So the equivalent thickness, air thickness of this window here is T over n. The actual thickness divided by the refractive index. So if you're building an optical system, and I've seen this so many times, even by people who knew better. I mean, you're laying out an optical system, and where's my image going to be? You put in this window, and the image is not where you thought it was, shifted here. If you just said, well, instead of thinking of this as a thickness T, if I think of it as only a thickness T over n, calculate where the image will be, then I'm okay. So just don't forget about this shift. It's so easy to do. I've seen it. I've seen that done so many times in designs of systems. They lay them out. You get the metal, you drill the holes in it, put the mounts in and stuff, and things are in the wrong location. The next one is equally bad. I mean, this is, I've seen this so many times in my life. A mistake made here because every interferometer has a beam splitter in it, and often a plain parallel plate beam splitter. So if I take a beam of light going along here, it's making an angle of incidence I with respect to this plate. Inside I prime, plate is thickness T. The beam coming out, if it's a collimated beam, I don't get any aberrations or anything, that's great. But the beam coming out is going to be shifted sideways. And you have to allow for that. How far is it shifted sideways? Well, you go through the calculation. It's D, the shift is thickness of the plate, cosine of I, that was the angle of incidence outside, times the tangent of I minus tangent I prime, the angle of incidence inside. And you plug in here Snell's law, and you get this mess right here for the displacement. Okay. And for small angles, you could take this mess here, and it becomes Ti n minus 1 over n. But I don't know. Now everyone has a computer. Why worry about small angles? Calculate what it really is. It turns out here there's something that's kind of useful. That if I put in that n is 1.5, and the angle of incidence is 45 degrees, which is so common, it turns out that D here will be approximately the thickness over 3. Okay. And just, again, that's something to remember, that T over 3, and you can impress your boss someday by that, maybe. I remember when I first got out of college, I had a job working in industry, and we were designing some interferometer. And I was working with a mechanical engineer. And I was going to calculate what this is. And this was so long ago, not only did we not have computers, didn't even have calculators. I know it's hard to believe, but there was a time in the world when we didn't have calculators. So how did I have to calculate this? A slide rule. But I was working with this mechanical engineer. And he just said, oh, well, it's going to be T over 3. And I go through all my calculations and stuff. Oh, it's T over 3. I thought, boy, is that mechanical engineer really smart, you know. And he was smart, but anyway, remember T over 3. Maybe you can impress someone someday with that. Well, if you have collimated light here, you don't get any aberrations. If the light's not collimated, you do get aberrations. And I hate putting non-collimated light through plane parallel plates. I just absolutely hate it because you always get aberrations. And if I'm at normal incidence, I'm just, well, I guess I show it here not at normal incidence, but if I'm at normal incidence, I'll get only spherical aberration. And if I'm at something other than normal incidence here, which I always am with a beam splitter, then I'm going to get coma and astigmatism. And I calculate here, or I gave the equation anyway for the distance between the focus for the marginal rays and the paraxial rays. But what is probably more useful is the wavefront aberration that you get here. And the third order wavefront aberration goes as T, the thickness, U to the fourth, U being the cone angle here, or half a cone angle, n squared minus 1 over 8n squared, or 8n cubed, I should say. And the last equation, which no one should ever memorize this equation, but there's a couple things about it that you want to kind of remember. One is, it's proportional to t, that's very easy to remember. Inversely proportional to the f number to the fourth power. And then we have something here, it depends upon the refractive index, n squared minus 1 over 128 n cubed. Small f numbers, bad problems. And I've seen this so many times. People just, such a simple thing, but people still insist on sending non-collimated beams through plane parallel plates. And if you have an F10, this is 10 to the fourth, maybe you're okay. If you have an F3, forget it. It just will kill you. It's just sending non-collimated beams through plane parallel plates. It's just a sin. It's a terrible thing to do. So it goes as 1 over the f number squared. If we look at this here, and this is kind of interesting, the n squared and the 128 n cubed. So, if n is 1, of course everything is great. As n becomes larger, then this becomes larger to some point, and then for n real large, this becomes small again. So if you go to a high index material, you're better off than a more common index material. And it turns out if you calculate this, where it's at a maximum, it's going to increase as n goes from 1 to the square root of 3. And then after the square root of 3, it's going to decrease. And of course, in the limit that n goes to infinity, it goes to 0. So that's kind of interesting. That it increases for a while and then decreases again. And the way I think about it, if I go to a large index, I mean, the rays, once they get inside the material, they're getting very close to the normal to the surface. And as the index goes to infinity, they would go right down the normal to the surface. And so in that case, you just have a mapping. So my plane parallel plate, you would just, for a very, very high index, you essentially have a mapping from the first surface to the second surface. And so the aberrations be very small. But for reasonable wavelengths, reasonable indices that you work with, I mean, this is just trouble. This is just trouble. Don't try to never send a non-collimated beam through a plane parallel plate. I mean, not only do you get spherical, but when you tip the plate, like you do with a beam splitter, you're going to get coma. Coma will go as 1 over the F number cubed. It will go linear with angle. And so if I have a tilted plane parallel plate in a beam, I'll get coma that's proportional to the angle that is tilted. And so one way to get rid of coma would be to put in 2 plates where the 2 plates are tipped in the opposite direction. So that cancels the coma. But what does that do to the spherical? Doubles the spherical. What does that do to the astigmatism? Astigmatism goes as a square of the angle, so it's going to double the astigmatism. So it gets rid of coma, but makes everything else worse. So if I were to ask you, when should you send a non-collimated beam of light through a plane parallel plate? The answer is never. Okay? Never. But people do it all the time. Yeah, sometimes you have to, but you try to avoid it. But people do it all the time. Okay, let's see here. Maybe that's about everything. I put in, lots of tables or lots of graphs here showing you how bad the aberrations would be. Point out for astigmatism, it goes as 1 over the F number squared. For coma, it's going to go as 1 over F number cubed. And for spherical, it goes as 1 over the F number to the 4th. So maybe F10, never F2. Okay. I have a section in here on aberrations of simple thin lenses. And I mean, I wrote this chapter a long time ago. I think this section here is not of a lot of importance anymore because everyone has a computer with Zemax or some lens design program on it. And I think that nowadays, I should ask you, how many of you use Zemax or Code 5 or, okay. So where did the Zemax come from? U of A. Oh. And Ken Moore, who was a student here, who took this class from me, took another class or 2 from me, was a student here, and sort of as a hobby, he began writing this lens design program. And now it's known as Zemax. And I tell you, every place I go in the world, they use Zemax. It is every place. So, I won't say much about this section, but the one thing maybe I should mention, say I have a plano-convex lens, And I'm using it to bring a collimated beam down to focus. Should the collimated beam be incident on the plano side or on the convex side? Or doesn't it make any difference? What? Collimated beam coming in. Okay, it should be incident on the curved side. And why? And so you're going to, well, you're going to have less spherical aberration if it's incident on the curved side. And what you really want is you're trying to distribute the bending of the light between the two sides. And if you had an incident on the plane side, you'd have no bending of the light, no refraction of the light on that side. And all the refraction would come on the other side. And if you put it on the curved side, then it's going to be shared between the two sides, and you'll get less spherical. And you can, that will drop out of this equation if you want to do that. And actually this gives you how you should bend it to minimize the spherical. But I remember when I first became a graduate student, that was one thing that was before then I thought it didn't matter which way you put the lens in, but it makes a big difference. Well, the next thing we're going to talk about here, we're going to go on and talk a little bit about conics and a little bit about A-spheres. And I think what I'll do, I think I'll stop at this point, and then we'll bring this up at the beginning of next class. And then next class we're finally going to get to the point where we're actually going to almost begin optical testing. So I'll see you, well, before I let you go, I have to ask you, I don't remember seeing any of you at the football game. Did I just miss you? Were you there and I lost you in the crowd? No. Okay, well, next class I'd like to have you know who we play this weekend in football.